Let's see how to construct a public key crypto system based on discrete logarithms. We will begin with key generation. The first step in key generation involves choosing a large prime number. We're going to call that prime number Q. Q is an element of the set of prime numbers. We're also going to need a generator. And we're going to call the generator G. This generator is an element of the set denoted by ZQ star. So let's unpack this notation. If we just had ZQ without this star, that would be telling us that we're dealing with the integers mod Q. So the integers mod this prime over here. But we are adding this star over here, and this star specifies that we're going to remove all the elements that are co-prime with Q. And because Q is prime, the only element that we have to remove is 0. So 0 is the same as Q, mod Q, because it's an integer multiple of Q. So we're just removing that 0 from the set. And this contains all of the integers from 1 up to Q minus 1. So that's what this is telling us over here. And this G over here is a generator for this cyclic group. So we have a prime and we have a generator. Now we have to choose a secret value. And we can denote this secret value as S0. And this secret value will be sourced from some of these numbers over here. But we're going to have even more restrictions. So we're not just going to remove 0, we're going to remove 1 and minus 1. So this secret is an element of the set of integers going from 2 up to Q minus 2. So we've excluded 1 and we've also excluded Q minus 1. Q minus 1 is the same as minus 1 mod Q. So those are the elements that we excluded, and these are our possible choices for this secret value. Now we're going to use this secret value to construct a public value. And we can call that public value P0. And we can construct this using the generator. So the generator is going to be over here. It's going to be the base, and then we're going to use this secret value as an exponent. So we're going to raise G to the power of S0. And we're going to do this mod Q. This is modular exponentiation. So this secret value is acting as an exponent, and it's giving us this public value over here. Now we have all the information necessary to construct the secret key and the public key. The secret key will be used to decrypt messages. So we can have the secret key over here. Secret key, or SK, is going to consist of this prime value, Q, and the secret value S0. So this is the secret key. Now let's have a look at the public key. So the public key, PK, is going to consist of several values. We're going to need to include this prime, Q. We also need to include the generator, G, and we also need to include this public value, P0. So we're sending 3 values in this public key. And this is being sent through a public channel. So we can imagine a public channel over here, and we're sending that to another participant. And now this other participant is going to do encryption. And this other participant is going to encrypt a secret message. So let's have a look at how encryption works. So encryption, we're going to start with the message. The message is an element of this set over here. So we're going to have Z, that's the integers, mod Q, and we're going to put this star over here to tell us that we're excluding 0. So if this Q over here was not prime, we might have to exclude other elements as well. And because Q is prime, the only element that we have to exclude is 0. So this message could be 1 all the way up to Q minus 1. Those are all of the possible integers that M could be. So that's what this notation is telling us. That's why we're putting this star over here. So m is not allowed to be 0. And this generator is also not allowed to be 0. So let's have a look at how we can perform encryption. So we're given this information in the public key, and we're going to do a similar procedure. We're going to pick a secret value, and then we're going to generate a public value. So let's have a look at this secret value, S1. We're going to choose S1 from this same set over here. So we have the options going from 2 all the way up to Q minus 2. So this is the set of all of the possible options that we can choose our secret from. And then we're going to generate a public value, P1, and that's going to be done in a similar way that we have over here. So we're going to use that generator, and we're going to exponentiate the generator with S1. So we're doing G raised to the power of S1 mod Q. So everything is being done mod this prime number Q. So we have a secret value, we have a public value, and we're also going to generate a key. And this key we're going to call K. And this K is going to be generated in the encryption step and the decryption step. It's actually going to be a shared key. And we can get this shared key over here by using this value P0 and raising it to the power of S1 mod Q. So you can see that we have P0 as the base and the exponent is S1. We're going to use a different technique to produce this K when we move over to decryption. But now we're left with one more step. We have to produce the ciphertext. And we can get the ciphertext from the message M by multiplying the message M by K. That's this key. And we're doing this multiplication mod Q. So to go from the message to the ciphertext, we multiply by this key, and we're doing this multiplication mod Q. Now we're going to send the ciphertext through a public channel. So this ciphertext is going through a public channel. What does the ciphertext include? So CT for ciphertext includes this value C, and it also includes this public value P1. We need this public value P1 so we can generate K over here. So for decryption, now let's move on to decryption. We're going to first generate that value K, which we have over here. And we can do that with this P1 and this S0. So K is equal to P1 raised to the power of S0 mod Q. S0 and Q are sourced from the secret key. So that's that secret key that was generated over here. And this value P1, that comes with the ciphertext. So that's being sent through the public channel from the other participant that is doing encryption. And now we have K. And this value of K is now going to allow us to turn the ciphertext C into the message. So how can we get the message M from the ciphertext? Well, we can multiply by the inverse of K, mod Q. So let's do that. Let's take C and multiply it by K inverse mod Q. So we've constructed K, then we need to find the multiplicative inverse of K, mod Q, and that's going to allow us to go from the ciphertext to the message. And that is the procedure. So we have key generation, encryption, and decryption. Decryption uses the secret key, encryption uses the public key. And the public key and ciphertext are all being sent through a public channel. That means adversaries can do cryptanalysis using the information that's available here. This is all publicly available information. This information over here involved in key generation and decryption, that's secret. So only this participant has access to that information. And the participant that is doing encryption, they have access to the message, they have access to S1, and they also have access to K. And they are broadcasting P1 and C. So P1 and C are publicly available. Now let's have a look at why we can construct K in two different ways. So this procedure where we can construct this key that is shared, that is actually known as Diffie-Hellman key exchange. And we're adapting Diffie-Hellman key exchange to create a public key crypto system. And this procedure is sometimes known as ElGamal encryption. So we're using that shared key that we've constructed to encrypt a secret message. And now let's have a look at why this value of K can be constructed in these two different ways. So K is equal to P1 to the power of S0. But what is P1? P1 was constructed from the generator. So we can rewrite P1 as G to the power of S1. And we're raising all this to the power of S0. And this is equivalent to the generator raised to the product S1, S0. Multiplication of these secret values is commutative. That means we can swap the order and we can rewrite this as S0, S1 in the exponent. And then we can regroup, and that's going to give us G to the power of S0, all raised to the power of S1. But what is this value, G to the power of S0? That is this public value, P0. So that was constructed in this key generation procedure. So that means we have P0 raised to the power of S1. And all of this is done mod Q. So you can see that this shared key can be generated with P1 and S0 or with P0 and S1. Another way to generate this value of K is to use the generator and raise it to the product of these secret values. But you need to have access to both of those secret values in order to use this technique. So this participant over here has only got access to S0. So that's why this participant has to use this technique to construct K. But the other participant, which is doing encryption, this participant has access to S1. So that's why this participant has to use S1 as the exponent. The public values, P0 and P1, they are publicly available. Everyone has access to them. Even adversaries have access to them. So what is stopping adversaries from getting these secret values? Well, it's actually the computational difficulty of the discrete logarithm problem. So let's rewrite these secret values in a slightly different form. We can rewrite them as logarithms, but they're not the typical logarithms that you might be used to. They are discrete logarithms, and these logarithms are done mod Q. So S0 can be written as log base G, that's the generator, of P0 mod Q. So this is a bit of an unusual notation, but it illustrates the point. What we're trying to say is that if we take the generator and exponentiate using S0 mod Q, that gives us the public value. What if we want to do the opposite? What if we have the public value and we want to find this secret exponent? Well, then we have to take the log base G of the public value mod Q. And we can write down a similar expression for S1. S1 is log base G of P1 mod Q. So we're making an assumption about the computational hardness of this discrete logarithm. So it's very quick to do modular exponentiation. So this procedure over here, this is modular exponentiation, and we're also doing modular exponentiation over here. That can be done very efficiently. But to do the reverse, to do the discrete logarithm and turn these public values into the secret values, that is computationally hard by assumption. So this computational hardness assumption of the discrete logarithm problem, that is the basis of this public key crypto system. How can we compromise this public key crypto system? Well, one way is actually to use quantum computers. So quantum computers have a specialized algorithm that we can run on them. And this algorithm is perfect for doing the discrete logarithm problem efficiently. So that means that that assumption of computational hardness of the discrete log problem might not hold. So we might have to challenge that assumption in the near future. That is under the assumption that we have access to large enough quantum computers that can perform the discrete logarithm algorithm. And that algorithm is closely related to Shor's factoring algorithm. There are other ways to perform cryptanalysis on this system. One way is to take advantage of the choices of these primes and generators. But these primes are really large in practice, so it is very difficult to perform cryptanalysis on this type of public key crypto system. So as long as we're only dealing with classical computers and we don't have access to quantum algorithms, this crypto system is safe. But as soon as we have access to quantum algorithms that can efficiently perform the discrete logarithm problem, then we can take this publicly available information, including the public key and the ciphertext, and we can use that to decrypt the message over here. Because the only thing that's stopping us from decrypting the message is that we don't have access to these secret values. We just need access to one of these secret values, and then we can compromise this entire crypto system.